In this class up till now, we've been doing neural nets in NeuralWorks. There's a toolbox in Matlab that is handy if you're coding already in Matlab and you want to create neural networks inside your code. You can do these as command level prompts as well, and that's what I'll show you today, is how to bring up Matlab and then you type commands to create networks and train them inside Matlab. So this is the neural net toolbox. It's a special toolbox you have to add to Matlab called the neural net toolbox. Starting off, we're going to talk about the architecture of the network. So the first thing we need to talk about is what does Matlab use for transfer functions. The thing that we've called a threshold, they call a hard limit. It's because it's a hard threshold or a hard limit or a step, threshold. Linear activation they call pure lin, so that's just a line, looks like that. What we call the sigmoid, that is bounded between 0 and 1, they call a log sig. And then the hyperbolic tangent that we use a lot, the tan h, goes from -1 to 1, they call the tan sig. The way that Matlab represents neurons and networks is through a diagram that I've copied below. As we create networks, I'll show you how to view the network and see the diagram. But pretty much it matches how we've been talking about it. You have an input vector p. It's a vector of values, and the dimension of p determines how many inputs, and it tells the network how many inputs there are. But p goes in, gets multiplied by a vector of weights. Now this is a single neuron, because in a layer, multiple neurons, this will be a matrix, but this is a weight vector, so the vector p gets multiplied by the vector w. A bias neuron sends in a bias value, v is the bias weight, adds all together, so this is just like we had before. It's the sum of the weights times the inputs plus the bias times the weight, so that's the plus here. And then that goes as a vector into a vector of activation functions, and then the output comes out here of the neuron. Alright, so layers of neurons, same picture. There's a shorthand notation that they use. Here is a vector of inputs. Here's the bias input 1. Here's the bias weight. And then here's the matrix of weight values that multiply p. So the weight matrix here multiplies each of the inputs here, and it gets added together, and then so this is a vector, and then there's a vector of activation functions here that then gives you a vector of values here. So then this becomes the outputs of this first layer, where there's multiple neurons, and then they multiply by another matrix of weights. So this is the weights connecting layer 1 to layer 2, hence the notation 2, 1 here. Another bias, so that's the weights connecting 1 to 2. You add up the weights times the input vector a1, that was the output of the previous layer. You end up with a vector of inputs here that go into a vector of activation functions that then give you another vector of outputs from that layer that then become the inputs to the next layer. So, and then you multiply by a weight matrix for the layer of connectivity between 2 and 3. Bias goes in, add together to get the net input here, apply the activation, and so you can keep going forward with as many layers as you want. We're going to start off easy here. We're going to do a linear network with 2 inputs and 1 output. So we're going to have 2 values, p1 and p2, as the inputs. There's going to be a bias. The weight matrix is really just going to be a 2 by 2. And we're just going to have a linear activation function to give a single output here. So the way you create that in Matlab is you say net, and net is a data structure defining everything about the network. It has the activation functions, how many inputs there are, how many outputs there are, even the learning rate, the learning rules, everything is stored in this data structure. And to create that, we're going to use a built-in function called newLin. It creates a new linear neural net, so automatically in here it assumes a linear activation function everywhere. And then here we give it a matrix of minimum and maximum values for each of the inputs. So we have 2 inputs. So input number 1 has a minimum of 1 and a max of 3. Input number 2 has a minimum of 1 and a maximum of 3. So we have to give it that so that it knows the scale of the values of the input. And then here we say we're only going to have 1 input or 1 output neuron. So the first thing we're going to do is jump to Matlab and create this network. So pop over to Matlab and, wrong thing there. I encourage you to pull up Matlab at this point if you're following along in the lecture, and type in the commands with me. So the first thing we're going to do here is to create that net. So we're going to type in net equals newLin, and then we're going to give it the min and max values. So 1 and 3, colon 1, 3. So that's going to create a matrix, and then we say there's only 1 output. Put a semicolon here to suppress the output of that. And we get a new network. If we want to see that data structure, we can just type net, and it gives us everything you want to know about that data structure here. Typically, we don't look at that too much. What's nicer is you can do view of net. Give you a minute to type that in. And then it's going to show a diagram of the network. So there's a picture of the network. There's 2 inputs. There's a weight matrix that that it created. In fact, we're going to have to create that here in a minute, but it's an empty weight matrix, a linear activation, and then we just have 1 output. All right, let's go back to the lecture notes. So we're going to assign some weights and a bias. Obviously we could learn as well, but I want to start out just assigning weights. So the net structure contains a substructure called IW, and it's indexed by 1, 1 because it's the weights from the inputs to layer 1. So that's the first and only layer here. And we're going to set those weights to 1, 2. And then we're going to set the bias weight. So we're going to do net.b of layer 1. And we're going to set the bias to 0. And we're going to create some inputs P. So we're going to create one input pair 1, 2, another one 2, 1, another one 2, 3, and another one 3, 1. We enter this as a matrix so that it pops the first input, the second input, the third input, and fourth input all as 1 instead of us doing it 4 different times. So here's the matrix that we're going to enter. And then we're going to simulate, in other words, run the network with a function called sim. Send it the data structure net and give it the vector of inputs, or the matrix of inputs P. And since the weights are 1, 2, the first input goes in and we get 1 multiplied by 1 and 2 multiplied by 2 and then added together, and it's a linear activation, so we get 5, or we should. If we send in a 2, 1, we multiply 2 times 1 and then 1 times 2, add them together, we should get 4. If we send in a 2 and a 3, we get 2 times 1 plus 3 times 1, just the inputs times the weights, so we should get 8 here, and for 3, 1 we should get 5. Alright, so we're going to go back to Matlab and do that, and then we'll move forward to training. So pull back Matlab onto your screen. We have the network structure defined, and now we're going to do the weights. Be careful of the syntax. I always sometimes miss doing the curly braces and do a bracket instead because it's on the same button. So there's where we're going to set our weights to be 1, 2. And if we don't suppress the output, we're going to get that data structure back. And then we're going to set the bias of layer 1 to 0. Let's suppress the net output. What did I do wrong? Oh, too many equal signs, so let's fix that. Don't know why that's there. Alright, so we got that right. And now we're going to create the input matrix. So we're going to have a 1, a 2, a 2, a 3, hit return, 2, 1, 3, 1, close bracket, hit return. And there's our inputs. We have an input of a 1, 2, a 2, 1, a 2, 3, and a 3, 1. Alright, I'll give you a second to catch up here to type that into your Matlab. But now we have our network created, our network weight set, our network bias weight set, and the input set P is created. And so now we can simulate our network and store the simulation results in a vector of a variable, not vector, a variable A. So we send it the network and the input's P. Now we hit sim, hit enter, and we get the correct values. We get 1 times 1 plus 2 times 2 is 4, so we get 5. These are the outputs that we should have gotten that we listed before. Alright, so to train, not only do we need inputs, which are in the vector P, but we're going to need target values. And so the target values we're going to say for each of these, we want 1, 2 input to give us a 4 instead of a 5. And we wanted the 2, 1 to give us a 5, and then we want a 7 and a 7 for the other inputs. So we do this with a function called train. We feed it the network data structure, P and T. And don't worry about doing this. I left it as the default. As I was practicing here, it works fine. The default is 1,000 epochs and a learning rate of 0.01. You can use this data structure command to change the number of epochs. And you can set the learning parameter, the learning rate, for this weight set, the weights from layer 1, all with this command. And then what we're going to do is after we train, we're going to simulate it to see if we get the target values that were specified up here. Okay, so let's go do that. So we're going to have to define our targets. 4, 5, 7, 7. And now we say net equals, and we do this because it's going to train and then return the trained data structure of net back to itself. You could always rename it if you wanted to. You could say net trained, but we're just going to train the same network and stick it back into itself. We have to feed it the inputs P and the targets T, as well as the network structure. It pops up this little graphical user interface, shows you the network up here, and it shows that it did 1,000 epochs, and the RMS error was 10 to the minus 6th. So looks like it trained. It said it stopped training because it reached the maximum epoch. So let's simulate it and see how it did. So we send in the data structure net, feed it the inputs, and we got a 4.0036 instead of a 4, a 5.0026 instead of a 5. You can see it got pretty close. It trained down to pretty close error. Alright, so what if we want to do backprop networks? So let's go back to the lecture notes here. So instead of a linear network, we want to do a full feed-forward network. So we're going to have 2 inputs. We're going to have a layer of weights. And we're going to tell it we want to do the hyperbolic tangent here, tan sig. Then we're going to have another layer of weights here, and then we have a linear output layer that's going to feed us that single output. So we're going to use this command here, and you'll notice that when we do this, Matlab will say, well, this is a depreciated form of the command. It still works, but I'll show you a newer way to do this that requires less inputs. But if you want to, you can do it this way, and you feed it a min-max matrix just like before of the inputs, and then you say, I want a hidden layer with 3 neurons and an output layer with 1. So this allows us to create multiple layers, and then we list the activation functions for each of the layers. So the layer with 3 neurons are going to be tan sig, and then the layer with 1 output neuron is linear. So that is how we tell it the activation functions we want here. And then this is the training algorithm we're going to use. This is train GD, which stands for gradient descent. So that's what's written there, is train GD, gradient descent. I'll show you some other algorithms in a bit that you can use instead. So the way we're doing this is we say, here's our inputs, min-max, so that tells us exactly how many inputs there are going to be, because we're listing a min and max value for 2 different inputs. Then we're going to say there's 3 neurons in the first layer and 1 in the second, and then we give it the activation functions and then say train using this method. The weights are initialized by new FF, so don't worry about that. If we wanted to do it again, we could say net equals a net of net, and that resets the weights to random numbers. So we're going to create this network, and then we can simulate the network by just putting in 1 set of inputs here and see how that works. So we'll do sim on that input set. And then if we want more than 1 input, we do it just like we did before, or we'll send in a matrix. And then here's what we're going to use for training. We're going to have this set of inputs, P, and this target values. And so when we put in a -1, 0, we want a -1 out, -1, 5 going in, -1 out. A 2 and a 0 going in, we get a 1. A 2 and a 5 going in, we get a 1. Another way you can do this is you can, instead of doing that min-max table by hand, you can tell it, okay, look at the matrix P of inputs and figure out the min-max by yourself. We still have to tell it how many neurons and what kind of activation functions we want in the training algorithm. Here we can tell it, we can set some parameters here. We can tell it to show every 50 epochs. We can set the learning rate to 0.05, number of epochs to 30, and we can set the goal to -1 times 10 to the -5. So here's our training set again we're going to use. Here's our target values, and we're going to stick the net after training back into its own structure, and then you can put another vector here, TR, that contains training information if you ever wanted to plot that. And then we're going to test it by simulating it after it's done and see if it works. Okay, so back to Matlab. So we're going to create a new feed-forward network. There's our matrix, get it right, there's our matrix of min and max values. Here's where we're going to tell it that it's a 3 hidden layer and a 1 output layer, and we're going to tell it what we want to do is tan sig for the hidden layer, pure lin for the output layer, We're good there. Close that off. And then here's train gradient descent. Close that off. Suppress the output. I think it looks good. Let's give it a try and see what happens. And it worked, but it says new FF used in an obsolete way. See help new FF to update calls to the new argument list. So we can do help new FF, and it spits out everything you ever wanted to know about this function. And it tells us that we could send it in the input matrix and the target values, and then the size of our hidden layer down here, and it will create the network for us, and it will default to tan sig for the hidden layers, and it will default to purelin for the output layer. So if you're willing to accept those defaults, you can just do this. And it even defaults to train LM, depending upon some additional arguments here. But we're going to go ahead and specify that. So I'll show you another way to create the network, the second way, and then we'll do this in a bit. But so far now we have a network already created. We can view it. And there it shows our two inputs, our first layer of 3 sigmoid activation functions, and output layer of linear that outputs 1 output. Okay, let's see what's next. We already created our network. We've already initialized the weights. We could create a very easy way to test this. We're just going to create one input that goes into here called P, and it's going to be 1 and 2. And we can sim that net with that input, and we get a number. That's kind of meaningless, but we can check it out and make sure that the net is actually working. So our training set now is going to be comprised of this training data that we listed before. Now I'm questioning whether I showed you this before. Yeah, I did, because we went through the lecture. So for a -1, 0, we want a -1. For a -1 and a 5, we want a -1. For a 2 and 0 going in, we want a 1. And a 2, 5 going in, we want a 1. Yeah, double checking. Okay, so we could train this net. And it trained to a good error tolerance. And you can see it gives really good answers. It gives -1, -1, 1, 1, and that gives us the right answer. And in fact, I didn't really even need to go through the steps of doing the show and the learning rate and the epochs and the goal. I just accepted the defaults. Okay, so the other way we could create this network is with the second method, where you say, I'm not going to tell you what the min-max is. You can figure it out from the input matrix P. I still need to say I want 3 neurons and 1 neuron output, and I'm going to specify the activation functions. Like this. So what's different than what we did before is it's figuring out the min-max all by itself. And what did I forget to do? Oh, I forgot my semicolon, or my, yeah, the apostrophe there. I think that should do it. Again, we're still using an antiquated or an obsolete call, but it still works. And then we could do and train that way. Notice that the error got slightly smaller because it figured out its own min-max table that optimizes it. And now we get really good results. Much better error because we let it figure out the optimal min-max table. And let's see, the last way to do this was with the updated version where we say new FF, we say here's our input matrix, here's our target values. I want 3 neurons in the hidden layer and default to everything else. Let's look and see what it created. It's the same network. It created 2 inputs, 3 hidden neurons, 1 output. Same network, just created in a much faster way where we've already told it the inputs and the targets. And then we can train this. And now let's simulate that. Wow, it didn't do very good at all, did it? Let me pause, see if I can figure out what I did wrong. Alright, sadly I can't figure out why that doesn't work. So ignore that new method of creating a network until you or I or we both figure it out. Alright, so let's wrap up the lecture here because we're almost done anyway. Other learning methods that you can specify in the new FF, we've been using train GD. You can do GDM, which adds momentum option. You can do GDA, which is an adaptive learning rate. You can do GDX, which is another adaptive method. You can do train RP, which is something called resilient backprop that just uses the sign of the derivatives rather than the actual error delta. There's something called conjugate gradient training, CGF, CGP, CGB, all of their different variations of conjugate gradient. There's something called SCG, which is scaled conjugate gradient. All different methods that people have developed. There's a quasi-Newton method because really we're minimizing this function that's the error. And if you remember, Newton's rule is a method for minimizing functions. There's a secant method called OSS. And then this is actually the default and best learning method for a lot of neural nets. It's called Levenberg-Marquardt. It's very powerful, but it uses a lot of CPU and memory. So if you have a giant network that needs a lot of memory, this thing may max out the memory on your PC and run slower. But ordinarily, this thing trains on the order of 1,000 times faster, that is number of epochs, than a lot of these other methods. Alright, so other than the glitch we had with the new way to create a network that didn't work, this is how you use the Matlab Toolbox to create networks inside Matlab.